So welcome to today's event. I'm Jackie Jones from Herefordshire Green Networks Building Sense, and we're delighted to be hosting Ellie Deacon-Smith and Matt Hayes from Arbor Architects today. And they're going to be speaking, as you know, about retrofit of traditional and heritage buildings. Now, this is particularly relevant in our part of the world. We, Herefordshire Green Network Building Sense, are part of the Future Ready Homes scheme, and that's running in Shropshire, Powys and Herefordshire. And that is in place really to try to build good levels of competence in retrofit. And one of the things that that scheme is offering to people in those three counties is the chance to have a free retrofit assessment, which is a very detailed piece of work. One of the things that we've observed with applications so far is that a lot of them are coming from people who are living in homes that are often very rural, in old traditional buildings, and they are particularly challenging. They're hard to heat. Everyone is different, and doing a full energy retrofit on them can be financially as well as technically challenging. But as we'll hear from our speakers today, there's a range of appropriate solutions for different situations. Now, Tony and I will, between us, put into the chat the links for Future Ready Homes, but it'll also be in the emails we'll send you. And just to let you know, we will be in touch by email with anything relevant to follow up. Some of you said you're a professional, and if you're a professional in this region, we'll also follow up to just let you know, give you the chance to get our regular newsletter that we just started. Good, so I'll stop share now. Ellie and Matt will start their share, and welcome.
Okay. Hello everyone. It's great that so many of you have joined today. So we are Matt and Ellie, and we're a team of 4 Arbor Architects, and we're based at the Shell store in Hereford. So we have a background in delivering mostly low carbon new build projects, and these range from private dwellings to community buildings and schools. And underpinning all of our work has been our passion for delivering healthy, low energy buildings that are adapted to their context and ultimately perform as well as they're intended to at the design stage. So increasingly though, we recognise that to be truly sustainable and to meet the challenge of the climate crisis that we face, we need to think about how we reuse and maintain our existing buildings. By doing so, of course, we're avoiding creating more waste and unnecessary new carbon emissions. And we also reduce the pressure on our finite natural resources. So we're going to talk to you today about retrofitting traditional buildings. And these are buildings built pre-1919, often with solid wall construction, that have some heritage significance. And we by no means have all the answers. Every heritage retrofit is unique, and we'll continue learning throughout our whole careers, no doubt. But we're happy to share our learning and show you a few case studies which demonstrate our approach and a little bit about what we've learned so far. So before we look at the case studies, we'll briefly look at the context we're working in and explain our approach. So the UK built environment, as I'm sure most of you will know, is currently responsible for 25% of total UK carbon emissions, and that's buildings and their infrastructure. So to get towards the government's target of zero carbon by 2050 and Herefordshire Council's more ambitious target of 2030, making our homes and workplaces more energy efficient is really crucial in achieving these goals. And what makes this all the more challenging perhaps is that 80% of buildings that will exist in 2050 already exist. So a major priority is decarbonising our existing stock alongside building high-performing new buildings. And the UK housing stock is one of the oldest in Europe, with 20% of our homes having been built pre-1919. So we can't ignore them. About 2% of our buildings in the UK are actually listed.
And we really like this quote by William Morris for the way that it sums up some of the intrinsic qualities of our historic buildings, the way that they're part of our evolving cultural heritage, the way that they embody the communities who made them and built them and occupy them, the way they add distinctiveness and meaning and quality to the places where people live. And obviously with all of this, a special approach is needed to ensure that these values are maintained for future generations when we're looking at retrofitting historic buildings. And so zooming out a little bit in terms of what are the aims of retrofit as a whole, and we've summarized these as three key kind of areas. The first one being this idea of the health, well-being and comfort of the occupants and users of a building. The second one being the idea of reducing the energy demand that the buildings take, and looking at whether low carbon energy sources can offer anything to the buildings. And then the final one is this idea of creating resilience to extreme changes in climatic conditions for our historic buildings. I guess it's worth noting that it's a widely held belief that some older buildings aren't energy efficient and they must be radically upgraded to improve their performance at all. And in reality, the situation is far more complicated than that. And assumptions about poor performance aren't always justified as black and white as that. The diagram starts to look at two different construction methods. The one on the right being the historic, traditional solid construction building, and the one on the left looking at a more modern, hermetically sealed equivalent. And I guess looking at this traditional, the historic building, it's when we're looking at any traditional solid stone or solid construction building, we're constantly thinking about moisture because of their ability to take up and release moisture through their fabric. And I suppose also connected to this is this idea that they're slower to heat up and cool down, giving them a kind of greater thermal inertia, which helps a little bit to prevent big fluctuations in humidity and temperature, which isn't the same for the modern hermetically sealed version. And I suppose with both of these two studies, energy and carbon performance of nearly all of historic buildings can be improved with one method or another. And what that's doing is driving them to be viable and useful now, but also in future for future generations. But striking the balance between benefit and harm isn't that easy, and getting the balance right and avoiding unintended consequences is best done with a holistic approach. And the approach we use is called the whole building approach. And this ensures that energy efficiency measures they're suitable, they're robust, and they're well integrated, and they're seen in the context of the project as a whole. So to go into that in a little bit more detail, with the three key retrofit drivers at the top: energy reduction, internal comfort, and climate resilience. These are the kind of categories that make up a whole building approach, and these form our analysis for any retrofit project we work on. So the first one, fabric measures, looks at insulation, draft proofing and air tightness, glazing conditions. It looks at the external fabric in terms of its rainwater protection, whether pointing is needed or guttering and roof repairs are needed. It also looks at the kind of wider condition of the building. And then with that, it tends to look at the use of the building and the form of the building. The next point down, services, heating and ventilation. So looking at what the heat sources are existing, what the controls are for those heat systems, both centrally and around the building. Ventilation, whether that's natural or mechanical, and realistically what it's doing in terms of thinking back about the use category, and then whether renewable energy sources can factor into this. The occupants and use is a really important factor for the whole building approach, because it tells you a little bit about the patterns of use, how the different spaces in a building are intended to be used, both now but also in the brief of what an occupant or a client is looking to achieve. Context and climate is almost kind of one of the most important, because it looks at the location of the building in terms of its kind of weather area. It also then looks at a kind of micro scale exposure to sun, rain and wind across the different seasons. The historic and community value is obviously essential for the buildings we're talking about today, and they are separate in terms of historic merit and community value, and we'll look at that in a little bit more detail. And then regulations is a really crucial part. You know, the buildings that we're working on sit within a very kind of strict regulation framework of planning permissions, listed building consents, building control, in amongst a whole host of others. And then funding is a really crucial one in terms of where the funding is coming from. Is it 100% sourced from the client, or are grants involved? Do we need to think about phasing in this kind of whole building approach? And then all of these determine the way in which a whole building approach should be carried out, what the options are, and also what the constraints are for its retrofit. So today we're going to look at three examples of where the whole building approach has driven three completely different approaches to retrofit. And I suppose it's worth at this point highlighting, as a practice, we take the view that doing the most you can where possible is the foundation of what we do. And that then means on other points, sometimes it's, you know, less is just fine. You know, if you're just then looking at maybe a one feature or two features, and then again, that then accommodates a little bit more when even less is fine too. You know, we're looking at maybe just a curtain or an improvement to a window is fine. And it's getting this proportionate response to the project.
So the first case study we're going to look at demonstrates this whole building approach in practice at the very early stages of a project. And this is a barn conversion that's currently a home, and it's located in the Brecon Beacons National Park. The home is currently really poorly performing. It's hard to heat, it's drafty, and it runs off an oil boiler. The young family who live there want to reduce their carbon footprint and make the home more comfortable and resilient for the longer term. So looking at the building's use over time, we discovered that it was originally a 19th century threshing barn with an attached cart shed and a number of lean-to animal shelters, all of which were removed when it was converted to a house in 1987. And this has resulted, as you can see in the top two images, in a slightly odd and unbalanced frontage elevation. The conversion also carved up the threshing barn space and made internal spaces quite dark and disconnected from the surrounding landscape. And a lot of the original lime mortar had been repointed with cement mortar on large areas of the front elevation, and poorly fitted windows and just a lack of insulation make the home really drafty and hard to heat. The location and orientation of a building makes a considerable difference to how the building performs and what can be done in the retrofit process. Specifically, where there's a lot of driven rain, good maintenance of the fabric is obviously really key, making sure that pointing is in good repair and gutters are working. If an elevation is exposed to a lot of sun, this can cause problems with internal wall insulation systems by pushing water into the building during the summer. This is effectively reverse condensation. And our site analysis for this project showed that the east and west elevations particularly were very exposed to wind-driven rain and excessive morning and evening sun in summer months. And for this reason, we'll have to consider weather protection and solar shading on these elevations. We also need to understand how the building was originally designed to work and where its heritage value lies within its community context. This is obviously indicated in planning terms by its location within a national park, and this has given us constraints in terms of how the building's appearance can be altered, but it doesn't tell us everything we need to know about its heritage or community value. So a sympathetic understanding and research is required to identify what is significant. The original purpose of this building was obviously a threshing barn. This is defined by the large opening through the centre part of the building, which you can see in the photo there that it's been completely blocked off. So there's an opportunity here, as well as improving the building's fabric performance and airtightness, to reinstate this central open space and to rebalance the elevations with external weather protection and shading structures. There are complex interrelationships between the different thermal elements of the building, the space, heating and ventilation systems, the use of the building and its context. And it's essential to understand how the building is designed to work and where any past alterations might have unbalanced this environmental system. If alterations are made to one element, then there may well be knock-on effects with other elements. And an example of this might be introducing better performing windows. The space heating demand is then reduced, so the heating system will need adjustment. Air leakage will be reduced, so additional ventilation might be required. And adjacent walls will become cooler in relation to the windows. So without good ventilation, the risk of condensation on the reveals is hugely increased. So for this reason, we undertake a building survey to establish as much as we can about how the building is working and where there may be any issues that need rectifying as part of the retrofit process. In this barn, our priorities are thermal upgrades and improving the airtightness. Moisture isn't really a problem at present, but that's probably due in large part to the fact the building is so drafty. So any alterations we make will need to be carefully managing this balance. So to fully understand how the building is performing, we use energy modelling to indicate which elements of the fabric are the poorest performing, and then we test different upgrade scenarios to work out which moves will have the highest impact on comfort and performance and offer the best value for money. An example is insulating the floor, which is relatively low risk on an existing solid floor, but it has a huge impact on energy performance. Whereas when we modelled upgrading double to triple glazing, this actually didn't have as big an impact perhaps as would be expected. But we concluded that if all the modelled upgrades we decided on with the client were carried out, then we can actually halve the energy demand of this home. So the conclusion of this whole building assessment shows that a number of fabric interventions will be possible. The cost and potential risk of each move is indicated by the coloured circles on the section. The green being the lower risk moves, going through amber and up to red, which are the higher risk and higher cost moves. So the simplest thing the client can do are things like thinking about which spaces in the house suit the different activities best. And an example of this might be moving a workspace to an area with high levels of natural light. Also things like ensuring external ground levels sit below the internal floor level to make sure water's running away from the building, and checking the energy rating on appliances. They're all things that can be done kind of quickly and cost effectively. And then we've looked at slightly higher risk, higher cost moves, which might be retaining the roof structure but insulating between and above the rafters. In this instance, we're raising the roof a little bit, but obviously keeping the structure in situ. And this provides significant upgrades in fabric performance. And it also allows the clients to expand their living space into the roof. We're taking out redundant chimney breasts, and this will reduce drafts and improve airtightness. And then the higher risk moves and higher cost moves include insulating the home internally. And then the sort of nose protrusion on the front can accommodate external insulation and overcladding. We're also replacing the windows where they're single glazed with double glazed units and adding a new roof light to improve the thermal performance and increase solar gains. And here's a couple of views of the moves we're making externally. We're adding shading structures which will rebalance the elevations and provide shading and weather protection to the most exposed elevations. And we also use modelling software that allows us to accurately model the proposed alterations and test how they catch the light and shade through the changing seasons and at different times of the day. So this process is not only about establishing the correct technical moves we need to make, but it's also the best design moves to make this a space that will work for our clients and also bring delight and joy into their lives.
Okay, so the next project we're going to look at is the Tin Barn project. And it's a series of barns located near Bath on the edge of Marshfield Conservation Area. The barns are curtilage listed as part of the setting to the original Grade 2 farmhouse to the north of the site. And the site's really important because it's identified as a transitional site from the rural agricultural landscape into the more formal village to the north. It's worth saying that the barn project is, out of all of the ones that we're looking at, the kind of most extreme retrofit. It's a deep retrofit in parts, and it's also new build in other elements due to the condition of the buildings. One of the most important things in terms of its whole building approach and heritage and community asset was this idea of, to the south of the site, there's a public footpath, and the barns are viewed in the context of the formal village. And the existing forms of the barns were deemed to be really important through conversations with the conservation officer. This defined nearly all of the architectural design and detailing in terms of maintaining an agricultural aesthetic. And it defined material use and fenestration and detailing, as well as other kind of key drivers. And so our initial analysis concluded that the level of retrofit we took to the barns varied across the site. So outlined in red are 2 interconnected barns, barn 2 and 3. And the structure for these required extensive rebuilding. And it basically concluded that we were able to achieve a far deeper retrofit here. And we started to investigate whether we could achieve the passive house EnerPHit level of energy performance. The smaller of the 3 barns, barn 1, was much more intact, which was good because the structure was a lot more there, but its size constraints were really limited by the fact that it used to be a kind of animal shelter. The brief and the use and occupants of the barn 1 defined it to be a workplace and store, and also the client's budget across the whole site also kind of determined that the level of retrofit in barn 1 would be deep retrofit, and less a lesser level than the rest of the site. So barn 1 on the left is the smallest stone building. It is the most intact out of the 3, but the stonework was in great need of repair, and the roof was almost collapsing, and any kind of openings had kind of fallen away in terms of windows and doors. The middle barn is the barn 2. It's a modern steel frame Dutch barn, and its structure is quite rudimentary and agricultural, so that held little architectural merit other than the overall form that it defined. And this was an important driver for the project. And then barn 3, the one on the right, was attached to barn 2, and the only bit that was still standing was this end gable wall, and a really lovely rounded corner as it met the south elevation, which was slowly falling away, as kind of indicated with the huge structural crack through the gable elevation. And so starting with barn 1 and our approach to that, if we start down at the slab level, we excavated out the old mud floor and installed an insulated raft slab. And the insulation wrapped the edges of the slab and then met the internal wall insulation, which then met the roof, new roof, which was fully filled with insulation, and then down to the walls, which were infilled with a timber frame and new windows and doors put into the openings. We were obviously dealing with an existing stone structure, which had varying levels externally and varying thicknesses of stone walls. So moisture was a really key driver for the design and detailing of this building. The picture on the left shows the first site visit we went to and the condition that the building was in. The middle picture then starts to look at partway through construction. So the insulated raft slab has been installed, the services have been put into the building, the new timber roof, an engineered timber joist has been installed, and the structure has been made good and shored up. And then externally, at the same time, we're looking at improving the breathability of the stone, so removing any cement mortars and damaged stonework and replacing it with a breathable lime mortar, and starting to make good all of the junctions. And then internally, we used a diathanite insulated cork render on all of the solid stone walls, and that acted both as our airtightness parge coat layer, but also the insulating layer on the inside face of the walls. And the reason we specified that product was to maintain this moisture breathability through the wall structure. And then that meets the roof build-up, which was fully filled with a warm cell recycled cellulose newspaper, which again has got that same breathability qualities in terms of the membranes either side of it. And then the image on the right starts to show, partway through construction, the lime plaster finish over the top of the diathanite insulated render. And then externally, large portions of the stone were repatched in with new stone, and details all kind of made good, keeping all the rest of the existing structure there, and repointing all of the stonework. And then the picture on the right shows partway through construction, the new roof being installed, and the openings infilled with new high-performing windows. So if we move across to barn 2 and 3, the strategy here was slightly different, and it started off with retaining all of the structure, even though that structure was in quite a poor state of repair. And so we ended up creating an insulated timber frame basically within the existing form that sat on the site. And that enabled the external visual to remain the same, whilst actually creating a really high performing internal environment. So again, starting down at the slab, we installed an ISOQUIC proprietary raft slab, with the insulation wrapping up underneath that, and then meeting the external walls, which were fully insulated new timber frame, which met the roof, and then back down to the roof of barn 3, which then had a slightly smaller insulated timber frame, which sat inside of the existing stonework. And we'll come on to the kind of details around that and the kind of trickier qualities of dealing with that. So the Dutch barn, you can see in the top left corner, was when we first visited site. And then partway through construction, you can see the timber frame being installed within that existing form, and all being kind of prefabricated inside so it can fit into the elevations. And then the barn 3 pictures start to show a little bit of the complexity of how we kept the existing structure and basically managed then how it sits with new structure to prevent thermal bridges and cold spots and condensation risk. And that was kind of further complicated by the way that the steel wasn't always in exactly the same position to the timber frame, just due to the kind of form and the structure that was there. So we ended up taking different strategies for how to thermally isolate it, and then to maintain a kind of draft-proof, airtight environment around it. And then internally, the top left image starts to show the green pro-passive airtightness board. And then externally, that was then covered up with a Solitex breathable membrane. Again, all of the kind of timber frames fully filled with a cellulose. So it's, again, moisture and breathability were really important. And then internally, we started to pull voids and light wells through the building so that the Dutch barn volume could be read internally, and starting to kind of play with how light moves around the spaces. And then on to barn 3, which had really suffered serious structural damage to years without a roof. And so the small amount of work, stone on the gable was shored up and retained, and then the rounded corner was also shored up and retained. And then the strategy then went to build an entire timber frame on a separate foundation system within that form, and create a breathable, ventilated strategy. So in terms of how we can kind of move moisture out of that cavity, and also manage then any moisture trying to get back into that timber frame. And I think the biggest thing that we learned from this was the need to be adaptable and also reactive to things on site. And so the kind of image on the right starts to show this new proprietary raft slab insulation fitting in around existing structure. And I think it varied a little bit in terms of things like measured building surveys being slightly inaccurate and having to change tack on site as we got further down the line. And then starting to look at the strategy on barn 3 of rebuilding the stonework on the exact kind of footprint of where the old foundation was sitting. And then the timber frame within that had some really complex junctions because of that, and how then it met the Dutch barn. And it required a huge effort from the whole team to make this a kind of draft-proof airtight envelope. But what it did do is it meant that we could achieve an air test result of 0.34 air changes per hour, which is way under the kind of EnerPHit standard that we were aiming at. So it's a really big achievement for the construction team. And then with this idea of improving the fabric to such a level of performance and airtightness, brought the need to really upgrade the services to the site. And that was two-pronged: one, to improve or ensure occupant comfort, but also the building longevity. So bringing in all of the kind of typical utilities, and then also putting in mechanical ventilation heat recovery units in each of the two barn 1 and then the combined barn 2 and 3, so that we were able to kind of manage the ventilation in an energy efficient way. And then in terms of the heat source, an air source heat pump was designed and specified so that it could provide the heating to barn 1, and then to barn 2 and 3 it also provided the heating and domestic hot water. And then that's all paired with kind of low energy fittings and fixtures, but also the provision for PVs in the future. And then what all this added up to was the idea that we were striving to achieve the exemplary passivized level of EnerPHit, which has an annual heating demand, space heating demand of 25, which we are all on track to achieve. And I suppose that created this kind of really stringent response on site, and this need to be adaptable and reactive to things quite quickly. And that meant not only updating architectural details and construction details, but also energy module details, and making sure the impacts were managed across. And then standing back on site, this idea of continuity importance was continuity of appearance was really important. And the idea that you read the kind of Dutch barn and the stone barns sitting around it, and little details which start to feel kind of agricultural in what they look like, and then hiding residential paraphernalia around the corner of the building forms. And then internally, starting to create really healthy, comfortable spaces with fresh air and natural light. We also specified bio-based materials and low VOC materials, and created little moments of joy, the way that light pools around a space, or little corners of the building to be occupied in different uses.
So we're just going to finish up by looking at a case study that's sort of almost the opposite end of the spectrum, really. This project is at really early stages of analysis, so we thought we'd just share the first thinking. It's an early 17th century farmhouse that's grade 2 listed. And the particular features of interest are the windows you see here on the frontage elevation, and also some timber panelling on the walls internally, one of which has an attached bench opposite a large hearth. Now, the building has really suffered from lack of investment and any sort of maintenance over the last century. And because of this, many of the original features of the building have been retained and therefore carry huge significance and heritage value. But on the flip side, this lack of investment has meant that the structure of the house is in a really poor state of repair and needs urgent attention to save it from dereliction. One of the major issues is that the house sits on top of a number of natural springs, which were originally channeled under the floor. But over time, these channels have become silted up and blocked, and now the floor is completely wet. There's also no insulation or central heating in the building at all, the only heat sources being a small ray burn in the kitchen and a couple of open fires. Now, many historic buildings have undergone alterations over the years that may have actually diminished their significance or put it completely at risk. And these harmful past alterations, though, may present opportunities for more sensitive refurbishment as part of wider energy saving improvements. So, for example, here, subsidence issues in the southern gable wall have been dealt with by installing some really large, ugly buttresses. They've been put in place as an ad hoc repair without planning or listed building consent, and they seriously detract from the original elevation. This subsidence will obviously necessitate significant structural repair and reconstruction. This allows us to remove the buttresses and reinstate a more authentic appearance to the southern elevation by removing the impermeable cement render and rebuilding the wall with breathable lime mortar. Additionally, a number of the windows to the rear of the farmhouse have been replaced with more modern frames, although they're still single glazed. There is an opportunity here to replace these with casement windows that match the original, but can be double glazed to make them more energy efficient. Oh, sorry. Clearly, though, the significance of the building means that the interventions we make have to be really carefully balanced in terms of the risk they cause to the heritage significance of the property. We need to consider a much more sort of light touch approach that identifies effective, cost-efficient and less risky measures that have a minimal impact on its heritage significance. The windows on the frontage are listed as an important part of the building's historic value, and this will likely prevent us from reglazing or even secondary glazing them. Instead, we have to look at traditional options for reducing heat loss through windows, such as blinds, curtains, or maybe shutters. These measures can result in significant reduction in heat loss without having any impact on the actual window itself. So lined curtains, for example, can reduce heat loss by 14%, while shutters on their own can reduce heat loss by 51%. And a combination of these options can reduce heat loss by as much as 62%, only 1% less than if we were installing secondary glazing. So I suppose to conclude, in our view, responsible retrofit of historic buildings based on a whole building approach is the way to achieve carbon reductions, enhance heritage value and improve occupant health and well-being. It's only through a deep understanding of context and a thorough analysis of the building's existing condition that we can implement the most appropriate retrofit strategy. Budget availability might necessitate a phased approach, but it needs to consider all proposed interventions holistically to achieve the best results and balance the risks. So thank you very much for listening, and if anyone would like to get in touch with us, please do, and you can follow us on social media with the links on this slide.
Thank you very, very much indeed. That's fascinating and interesting to see those different examples as well, different building types and taking different approaches as well. My colleague Tony is going to be dealing with questions. Tony, are you able to pick up on that yet, or do you want to hold on a moment?
No, I'm ready and willing.
He's ready and willing. So yeah, please do put more questions into the chat, and I'll hand over to Tony. Thank you very much.
Okay, hi everybody. Just to reinforce, Future Ready Homes is still open for business. We have energy surveys and other things going on, so do get in touch. I put in a link into the chat if you want to use that and apply. First question, I thought a useful place to start. Ali, could you give us a quick run through that you mentioned EnerPHit a number of times. What does EnerPHit mean? What is it in layman's terms?
So that's a very good question. EnerPHit is a standard from the Passive House Institute, which applies to existing buildings. It's very much related to the Passive House standard. It uses the same approach to building physics, concentrating on getting the energy demand of the building as low as it possibly can. But it accepts that when you're working with existing buildings, you're going to be dealing with more complex junctions that exist in the building, and therefore you're quite likely to have more thermal bridges than if you were building this building from scratch. So the targets are slightly relaxed to enable you to overcome those issues and achieve what is still an incredibly stringent performance measure and results in a very low energy building.
Can you remind us what the targets are in?
Yeah, so in terms of the targets, I guess the one metric to look at is the space heating annual heating demand. And if we just take, a really bad leaky building, it's going to be in the region of about 300 kilowatt hours per meter square per annum. The EnerPHit standard is 25. So you can see the vast reduction from 300 down to 25. I mean, they're obviously the polar ends. Old buildings aren't always 300, they're whatever they are. The air tightness is detailed at 1 air changes per hour, whereas the Passive House is at 0.6. And building reg is obviously a lot higher than that, depending on whether it's a new build or whatever. And then there are other metrics that you kind of need to achieve.
Okay. Thank you. So Jackie was asking, there's often a case for combining energy retrofit with a remodel of a building. It was certainly the case with the second example that you gave us, that was essentially a rebuild, new build.
Yes. Yeah, and I think it goes back to this idea that actually in that initial analysis, it's often the case that alterations have been made in the past on quite an ad hoc basis, and they might in themselves have upset the kind of balance of the original building and need unpicking. So there's the kind of rectifying the mistakes of the past, but then also, you know, often our clients approach us and they've got particular requirements for family space that doesn't fit into the building as it exists. So we take that kind of holistic approach that we're trying to resolve the technical issues, but we're also working with them to really try and understand their brief and see how we can design the spaces at the same time to achieve exactly what they want and need.
Okay, just going back to the EnerPHit for a moment, we had a question from Howard. Are you using PHPP, which is a passive house planning package, or is there some different energy modeling tool that you're using?
Yeah, so we do use PHPP in-house. We also use another related software called DesignPH, which is a SketchUp plugin developed by the Passive House Institute. Both of those two things are kind of, they give you similar outputs in terms of energy. We also work with other consultants who can do kind of complex thermal bridge calculations and more detailed kind of energy analysis. So it just depends. Each project is different in terms of what you need.
Yeah,
okay.
I guess it's often at the early stages, you know, design stages, right from concept, we're modelling in DesignPH and testing solutions, and then as it progresses, it might go into PHPP and you know, further from there.
Okay, we've got a much more straightforward question here. Did you need to underpin the stone walls? I'm going to expand it out a bit. Are we talking huge amounts of concrete, or did you use limecrete or something with a lower carbon footprint? And there was a connected question, which was about underfloor heat. This is the second, you know, the big rebuild that we're talking about. Clearly, was underfloor heating installed at the same time?
So in terms of the walls, it was something we accounted for in our initial kind of cost models, underpinning all the structures, and basically investigating it with the structural engineer and trial pits determined that they didn't need underpinning. They were sitting so close to the bedrock that they were in a good condition. But I think it's worth saying that yeah, each project's different, and I think it's safe to assume that the underpinning is likely to be required where you're making, you know, big structural improvements. That said, we did go through and do quite a lot of helibar tying the structures back together because they were kind of peeling away. So we didn't underpin the structures as such, but we did tie them back together. And underfloor heating was explored, but it was kind of discounted from the client's point of view. It wasn't something they wanted to invest in, even though it's a really good pairing with kind of renewable heat sources like the air source heat pump that we had in because of the lower flow rate temperatures. But in the end, they went with some just simple slick panel radiators.
And what type of concrete were we?
Yes, concrete. Yeah, we explored limecrete, and we really want to use limecrete, but on this project it wasn't the case. So we went with we've got a really good structural engineer who's really keen to reduce concrete use. So the specification of it was detailed as minimal as it could be, and the mix was obviously as sustainable as it could be, but there is obviously still concrete in there in terms of that build up. And I think that again, each project is completely different and has completely different drivers and constraints. In the barn project, the structure was working incredibly hard because we were basically holding up old structure and putting in new structure, and all of that basically determined the foundation build up. I think in some of the other case studies we've looked at, a limecrete floor from someone like Timawa built up on a kind of Gloucor type insulation system, it is exactly the right thing to do, where we haven't got those other constraints on the project.
Okay, we've got another materials type question about diathanite. How does the cost compare with traditional dry lining? How can you meet building regs for insulation using this material? So
it is worth saying, out of the insulated renders, diathanite is on the upper end of the expense. That's because the kind of lambda value of it is as high performing as something like a wood fibre board. I don't know what the exact comparison is between dry lining and that. We discounted going for a dry lining or a wood fibre type construction because we wanted to create a completely homogeneous build-up through the wall, so that we were going to best manage moisture and varying ground levels. That said, on other projects we have used wood fibre boards and dry lining type constructions. I suppose it's getting, and it's something we have explored, getting the balance right between what the cost of the actual material and installation is versus the kind of lambda value, and something from a diathanite, upper end of the performance and cost, all the way down to something like an EcoCork insulate and render, which has got a poorer lambda value but actually can half the U value of a brick built wall kind of thing. So
I think we may need an explanation of what a lambda value is, not least for me.
Sorry, nothing to do with sheep. It's the thermal conductivity of the material taken through a meter of it. So diathanite's got a much lower lambda value than aluminium, because aluminium just washes the energy through it, and steel, that kind of thing. Sorry. So
it's a different way of looking at a U value, in other words.
Yes, but it doesn't look at an overall build-up, it just looks at a material. And so when you're looking at like insulation, like Rockwool will tell you our lambda value is 0.034. And where you look at Kingspan, they'll say, well, our lambda value is 0.024. So it's just a way of just comparing the thermal performance of the material itself.
Right. Okay. Thank you very much. We've got a question about how did you tackle utility bridging? I was very interested to see the vast amount of cabling and stuff that was going in.
Yes, and again, most of that cabling and incoming services went into barn 1, where the use of it was lesser performing than the other 2 barns. So with that whole building approach, we didn't basically need to then tackle it in the same way we would have if it was higher up in the agenda. Whereas in barn 2 and 3, we limited any penetrations through the slab to basically one saw vent pipe, which was then insulated all the way through from slab through to the top of the roof. And then other services were limited to either coming through a kind of airtight grommet through the wall, or much smaller diameter rigid ducts into the slab. And then obviously they were part of that overall calculation of the thermal bridges kind of allowed for in the design.
Okay, great. Thank you very much. We have a question for everybody. Can we have the slides for the presentation? As ever, this is recorded. The slides are part of that recording, and therefore it'll be available on the HGN website and on the YouTube channel. So get your family and friends to watch at a later date if you like. Okay, there's a question here about water. Can you please explain what you have done on the ground level of the buildings? It was covered in dark grey. You said it was to deal with water at ground level, something to do with direction of travel of rainwater. Does that make sense?
It's on Langatov, isn't it?
Yes, I think that was referring perhaps to the section we showed. I think in that instance, the ground level around part of the barn had been artificially raised, so that it was essentially level with the floor finish inside, and that was causing a bit of a problem with water coming into the building when there was heavy rain events. So one of the simple things that the clients could do was actually just to remove some of that concrete that had been built up outside and lower the ground level so that it was lower than the floor inside. And I think often you see this on Victorian homes, for example, where the ground level just over the years has been built up, and sometimes it comes above the DPC, the damp proof course in the wall, and then moisture can become a real problem. It gets into the brickwork and it can rise up into the walls themselves. So checking that the ground levels haven't risen too high is key to solving that problem.
And I suppose, again, like a broken record, each project is different, because on that particular project, we knew there was a damp-proof membrane underneath a 1980s floor. So we knew that moisture coming up through the slab wasn't an issue. Whereas in other ones, you know, it's a different scenario. There's maybe a ventilated suspended timber floor, or a solid, you know, on-earth floor.
Right, okay, we've got more of a general question here, and probably a difficult one, and one I suspect you have to answer with your clients. In terms of targets, what do you normally go for? Are you looking at minimum standards, good practice, or zero carbon? A related question, in terms of whole life performance, what's the main purpose? Is it the embodied impact of the materials to build, or is it the operational, you know, carbon footprint going forward, the operational footprint of the building?
Yeah, I think that is a really good question, and it's one we've put quite a lot of research into over the last few years, because I suppose our background was a lot of just looking at operational carbon, but because of the climate crisis and our need to just reduce carbon as quickly as we possibly can, we have to be considering embodied carbon as well. And so that has become for us much more of a focus. And we've also been thinking a lot more about circular economy systems, and that carries through into all of our detailing now. And we're making sure that everything we build can be deconstructed and reused. And examples of this are, we will always avoid now hybrid materials, things that have been fused together with glues, and at the end of their life you can't do anything with them except chuck them in a skip. Whereas if you're using bio-based materials and materials that can be mechanically fixed and perhaps pulled apart and reused, then you're significantly extending their life and reducing waste and embodied carbon emissions. So yeah, we are increasingly, and I suppose it's something we explore with each of our clients individually. We'll talk about all these issues with them, and then we work out through this kind of process of assessing the context, the brief, their budget, you know, which level we might take it to, and which certification routes we might go down.
And I suppose there are some really great ways of doing that. Obviously, building regulations is your minimal legal performance, and then beyond that, there are really great ones. You know, the AECB have got some really great standards, and then the Passive House Institute have also got standards that, you know, go beyond just the operational energy into kind of renewables and being positive in terms of their impact on the site.
Okay, thank you. That's really interesting. Really good to think through. Yes, reusability of materials going forward. Right, finally, after about 20 minutes of questions, we've come up against cost, which I knew was going to come up because I was getting a bit nervous as you were talking. Clearly, a whole house approach is important, says Alan, but cost is also a major factor. Even an energy assessment costs a lot unless you get a free one through Future Ready Homes. Are there no regret measures you could recommend if people don't have the money to go all the way for what we call deep retrofit?
Yeah, there definitely are. And actually, interestingly, the AECB is about to publish more information about their level 1 retrofit, which, you know, is focused on people in exactly that position. And I think, interestingly, one of the things they're going to be recommending is the idea that you might tackle your heating system, decarbonising your heating system first, and there are, you know, grants available to help towards the cost of that. And even if you don't have the money to improve the thermal performance or airtightness of your home in the first instance, they've kind of established now that even if your air source heat pump is oversized to deal with the property when it's leaky and inefficient, later down the line, if it's retrofitted, it's not too much of a problem that it might have been oversized originally. But I mean, you know, also some of the measures we touched on in the case study, for example, you know, just putting in lined curtains or carpets to reduce the drafts, you know, it does have a significant impact.
And then another thing that we found is just looking at what your house is. So look at what your heating system is. Look at, you know, where the controls are for that heating system in terms of its, you know, it's typically on the boiler in a cupboard in a not the most accessible part of the house. So, you know, just, you know, a couple of £100 to improve that, so it becomes something more manageable, something more controllable in terms of you know, there's loads of systems like Atmo or Nest where you can control your heating at the, you know, the touch of a button, and just those little things can make huge differences in having more control over your heating system. Putting in thermostatic radiator valves in around the different parts of the house so that you're controlling where the heating goes. You know, they're quite small costs when you compare it to a deep retrofit, but they make a huge difference to the kind of energy demand. And then that kind of extends out to looking at, you know, your other appliances, you know, what their efficiencies and how what their kind of demand is on the energy of the house.
Okay, thank you. Right, we've got a specific question about actually, no, I'm gonna throw that question at you myself. The question I have to ask, which is what I'm trying to answer through the Future Ready Homes project, is how do we get to retrofit at scale? How do we deliver it more rapidly and at greater scale as we work towards net zero? I presume the sort of projects you've shown us, I mean, I love the painstaking approach and the attention to detail, and it's obviously magnificent stuff, but it strikes me it costs not only loads of money, but loads of time. So have you got any thoughts about how, if we are talking about 20% of the homes in the country were built pre-1919, how we, you know, we can't lavish 2 years on a single property, or you know, we're all going to be underwater. Any thoughts on that? Sorry, that's not a very
it's a massive question,
clear question,
you know, that needs to be tackled really quickly. And I suppose, you know, skills, it's training. We need, there is just not enough people at any level, at the kind of design team professionals or the construction professionals and installers that are doing this. So, you know, there's got to be a massive push to upskill people so that we can meet that challenge. And I suppose, you know, we are very much part of the kind of learning wave, aren't we? You know, so we're lucky to have these projects to kind of upskill on, but I think, you know, every architect needs to be doing it, and every builder needs to be getting involved in these projects.
And I think the crucial thing with that is that the balance is right, so that we're not actually causing harm either to, you know, heritage assets, internal environments, because I think we haven't touched on it today, but inevitably there are risks that come with making improvements to existing buildings and retrofitting them. You know, like improving the airtightness on a window and getting rid of the drafts and making it more airtight across a building is great in terms of your energy demand, but it's not good if you then don't tackle ventilation, and suddenly you've got a kind of stuffy environment where that you're not ventilating properly, and that almost applies to everything around that whole building approach. Adding an internal insulation is one of the questions, someone asking about wood fibre boards. Yes, you have to be very careful where you insulate and how you insulate, because you're basically dealing with moisture, and what we don't want to do is be making the mistakes of the past where cavities are fully filled with insulation and then moisture starts bridging. And I think that's why we're really keen on this idea of a whole building approach. You tackle, you look at the whole thing, you look at where the wind-driven rain is, you look at how the buildings are used, you look at where all the furniture is stored up against walls, and so that you can start to basically design out that risk so that you can keep the internal environments really comfortable and healthy, and you can still reduce the energy demand both now, but also, managing it in the future.
Okay, I'm going to push on this need to scale up. I'm going to ask the brutal question, I'm afraid, of a couple of heritage experts, which is there any discussion, is there any likelihood of levels of heritage protection actually being reduced, where as I think you were saying, there's got to be a balance between harm to heritage on the one side and the benefit to the planet on the other side. If we decide at, who knows, at 2041 that we're not getting down the road to zero carbon fast enough, are we going to tip those scales? I'm sitting here in a terrace of Victorian homes in a conservation area, and vast numbers of my neighbours have got dreadfully leaky single glazed sash windows facing the street, and enormous carbon footprints and energy bills as a result. If those windows are protected and you're not allowed to touch them, when are we going to start making some harsh decisions? Sorry, that's another difficult question.
Yeah, no, it's a big question, and I think there probably is quite a strong case to perhaps be a bit more pragmatic and relax some of those requirements where we can. But I guess it's also about zooming out and looking holistically, because if we say the AECB highlight that we're meant to be reducing carbon by about 50% in our buildings, but if you can go further than that in the buildings where you perhaps make some allowance for those few buildings where you really can't, and heritage value is so significant. Yeah. So you've got to consider the whole of the UK housing stock as one, essentially, to then kind of play off perhaps more carbon savings where you can and less where you really can't.
Okay, let's pick up Roy's question about wood fibre, which you mentioned. Say I have a 17th century farmhouse where there is an inherent danger of damp in the lower part of the walls, also a zone of interstitial condensation, and thus a danger of dry rot. What does Roy need to do there?
Yeah, that's a good question. It's a tricky one, and it highlights the kind of element of risk perfectly. And so I guess it's doing the whole building approach. It's looking at what is happening with that fabric. Where is that moisture coming from? Because it will be coming from a whole host of sources, from your kettle and your shower and your wind-driven rain and your rising damp, and it's making sure that whatever we do, we get the appropriate response. And sometimes that means getting a sample of the stone sent off and analysed just to work out how porous it is. If the stone, I'm presuming it's stone, is really porous, then it might be looking at other methods. What do we need to do, something to make the outside of the building a little bit hydrophobic, so the water just runs away rather than soaking through it. It's kind of analysing it so that you can design out the risk.
Okay, great. Quick question from Dan. Does EnerPHit certification need to be applied for during the retrofit, or can it be dished out, done retrospectively?
That was about the EnerPHit.
Yeah.
That's a good question. We've always, all of our passive house and EnerPHit projects have been done at the, you design it at the initial stage and then you see it all the way through. It's unlikely that you do something and then it does meet all those criteria afterwards.
And it requires, certification process requires quite a lot of evidence, and that's evidence of how things have been put together on site and what materials have been actually installed, and all of that involves collecting a lot of data that's compiled and sent to the Institute for certification. So I imagine it would be very, very challenging to do retrofit.
Possible, I think.
Yeah, possible.
But challenging.
Depending on the records you've kept, I guess.
Okay, so talking about planning a whole project, Jackie points out many of the government retrofit programs have pushed on specific single retrofit measures, such as we have the boiler upgrade scheme at the moment, which is available for heat pumps. We know that not everyone can necessarily do a full retrofit, but would you agree that having a whole retrofit plan that can be implemented gradually is important? I think one of the other contributors mentioned no regrets retrofit. Thoughts on that?
Definitely, I think that's it. And having that whole building approach and then a plan to implement things means that you're likely to do the right things in the right stages. And I think that idea that you phase a building when you're not doing a deep retrofit, and I think that has to be the more likely scenario that people find themselves in. They're going to be living in their houses and buildings whilst they are going to be repaired or slowly upgraded. But having that overall holistic analysis at the beginning and then a plan which picks up all of that is essential.
Yeah, okay, thank you. Another question about secondary double glazing is the question. I think that means secondary glazing. How do you rate secondary glazing as a means of improving energy efficiency in historic buildings where the original original windows need to be retained? Personally, I've had good experience, but I hear some experience problems of condensation.
Yeah, and
depends on the quality of the secondary glazing, I expect.
Yeah, and I guess again it goes back to that sort of considering everything that's interlinked with that, because of course you'll be making the window more efficient, it becomes warmer, so then you have to consider the reveals, so the walls coming into your window will suddenly be colder than your window itself, and that means that any moisture in the air will collect there. So you've got to consider at the same time that you're improving your window performance, how are you dealing with moisture in the air? That's improving your ventilation system as well. And it might be that you look at, how do you insulate your walls and make sure that the walls around the building are upgraded at the same time so that they're not colder.
And I think that's one of the really interesting bits of, you think retrofit, you think upgrading, and the windows are an obvious one because they're so poor performing in a lot of listed and heritage buildings. And I think just, the idea of curtains sounds like, oh, that doesn't do anything, but I mean, it's been proven to, make a difference. And when Ellie went through that kind of process of, you could add shutters with a thin layer of insulating material, and suddenly we're actually at near enough the same performance as a secondary glazing system. Because I think the other thing to think about in that is the use of the windows and whether that then starts to move away or change it. And I think it's getting the balance right, isn't it, of what the harm is to the window and improving the performance of it.
Okay, we're just drawing to the end now. Sorry, my question's just moved. I've just had a question about, do you have any experience of improving the thermal performance of cob walls? I would have thought that the thermal performance of cob was pretty good. I'm particularly interested in the idea that the stone plinth will have a much higher U value than the cob.
We haven't actually worked on cob. We'd absolutely love to. Yes, and I think it's worth saying that there's something really beautiful and interesting in historic buildings, which is their makeup and their fabric and their material structures and how they regulate moisture. and that just is not picked up in something like an EPC or a you know, even, you know, PHPP deals with it to an extent, but it's not, you know, it's not completely 3D and all seeing. And there's a bit of a lag at the moment where the regulation and technology isn't as good as it should be for, you know, working at these things. And that's where we will then go and work with, you know, external consultants and lab testing for materials.
Okay, another quick question about windows. Would you agree that having original windows refurbished can be a useful step in some buildings where they can't be replaced? Yes, presumably is the answer to that.
Definitely, yeah. And I think that the projects though is, you know, seeing alterations as an opportunity is a really good one. When things have been slightly, you know, tweaked in the past, they're an obvious place to maybe improve.
Right, in my grade 2 listed terrace, we've installed temporary perspex sheets over the sash windows held in place by magnetic strips. It has had a drastic improvement. Yeah, temporarily they can be detached, perhaps now as the spring weather gets better. Who are the main organizations pushing this agenda? Do they collaborate with each other sufficiently? Well, that's a big question and a very good one. Well, the AECB is one which you've already mentioned. I think we could talk for some hours about that, so let's not go there. The question that I've got to ask though, which was asked by somebody else, is can we have some indication of cost per square meter? It'd be very interesting to know of the case studies that you've presented. What was the price tag, but that may be confidential.
Unfortunately, it is confidential. I mean, to give you exact figures, it would be. I think the project where we were doing a deep retrofit and new build responds. You know, it's almost equal to it's a new build meter squared rate, which for a passive house you're looking at around yeah, £2,000 to £3,000 per meter squared. That's for a new build, you know, exemplary performing high-end building. But I think each project are different, and the two other projects that we talked about are at their analysis and planning stages. So we don't have the kind of cost details for them yet. But I guess it's just there are the balance, you know, of getting that right across projects, you know, that can vary, and there are different materials and specifications and elements you can pick up on to meet the budget, and the budget is a key driver.
Yeah. Okay. I'll just I'll let you off the hook there. Thank you very much for the presentation and for answering so many different questions. Just a quick point from Roy. Historic England have considerable advice on making historic buildings more thermally efficient. They have excellent guidance publications on the Historic England website.
Definitely. That's a really and the Sustainable Building, Traditional Buildings Alliance also has got some really great guidance, and they combine, you know, different bits from Scotland and Wales and the particular bits where, you know, they need to come together.
Okay, at that point, I will wrap up the Q&A. Thank you everyone for your excellent questions and for hanging on, and I'll hand back to Jackie.
Yeah, well, thank you very much, Tony. Thanks, Ellie and Matt again, and for everyone who put in the questions. We will be back in touch with you, let you know what else is going on. And of course, if you find that you've got questions after the event that you want to ask of Ellie and Matt, send them to buildingsense@hgnetwork.org and we'll happily forward them for you. And just to repeat, the presentation will be online and available, and we'll be back in touch. So thank you. I'm just thinking of the people who are going to be living in those beautiful spaces that you're making with those, what is it, moments of delight, I think. So we all need moments of delight, and yeah, wish you many more today. Thank you. Thanks, everybody.
Thank you very much.
Thank you. Bye-bye.
Bye-bye.